Swayam Prabha. Digital India. Educated India.
Now we are going to go ahead and solve several different problems on bending moment diagrams and shear force diagrams, and we'll travel through some very easy problems to some more complicated ones so that you have a gradual progression in learning to draw these diagrams for the different types of beams, for the different types of loadings. Now what I highly recommend for you is to go and grab a notebook and a pen, and for the first few examples just draw along as we solve these problems during the lectures, and for the later problems maybe you can take a look at the problem, try to solve it on your own, and if you're stuck somewhere or if the final diagram does not matches in the solution problem, then come and take a look at the videos, right? So let's go ahead and dive in for the first problem. So this problem right here, it shows you a simply supported beam. So this is the easiest problem that you can start with for a first course on drawing bending moment diagrams and shear force diagrams. You have a simply supported beam supported at A, a pin support at A, and a roller support at B, and you have a load P which is acting at a distance A over here. Now for this one we have to draw a shear force diagram and bending moment diagram, and before we do that, of course, we have to first find what are the reactions, and from this one I'm not going to go ahead and solve and calculate. You can easily tell that for this particular case your the reaction A, RA, is going to be P times B by L, and RB is going to be P times A divided by L over here, right? Now once you have the reactions, you essentially know the whole system. You know the loads which are acting, what are the reactions which are happening, and those are important precursors before you draw the shear force and the bending moment diagram. Without them it is not possible to draw, because then you will not know how the stress, how the forces are changing along the length of the beam that is there, right? So to draw the shear force diagram and the bending moment diagram, I'm going to draw the same beam twice, one for the shear force and one for the bending moment over here. So let me go ahead and draw that. This is the same beam. I'm going to use this for the shear force diagram, and I'm going to use this one for the bending moment diagram over here. Right now, if you take a look at this beam, typically where do you take these sections, that where you find these internal shear forces, internal bending moments? Remember from our previous discussions that you usually take these sections wherever you have points of discontinuities and so on. So here you have a point load at the very end, you have another point load here, another point load here. So in between these point loads are the ideal places to take your section. So the first section you may be taking around here, and the second section may be this. So let me just mark them. This is 1 and say this is 2 over here, right? So now what we are going to do, we are going to take these individual sections and we will find what are the internal shear force and internal bending moment which is acting over there. Now remember that you can take these sections or these cut sections either from the left to right or right to left, up to you, and you will see it's often a matter of convenience that sometimes your calculations gets heavily simplified if you are taking section either right to left or left to right. But here let's start by taking from left to right and see where we end up with, right? So for the section 1, if I have to write for the expressions that we get on the free body diagram for the section 1 that we have over here. So section 1 meaning that your x, this x lies between A to this point. So let's go ahead and mark this point as well. Let's call this C. So x lies between point A to point C over here. So let's just write it over here that you have your x which goes from A to C. So now that you have this over here, and let's draw the beam. Let's draw the beam. In the beam what I have, so this is my point A. I'm going from my left part of the beam to the right part of the beam. So from A I have this reaction which is still there, which is my PB over L. I have from this reaction to where I've cut this section, maybe just to the right of A and just to the left of C, I don't have any other loads, so I'm not going to draw anything on top of the beam. But at the very end over here, I'm going to mark my internal shear force and internal bending moment, right? Now remember, since I am going from left to right, my positive convention on the nature of action, what the shear and the bending imposes, is that my shear tries to rotate my beam in a clockwise manner. So my positive direction for shear would be this V over here, and the positive direction for the moment is the one which tries to bend your beam into a trough, or it causes a sagging effect. So this is my positive M over here, right? So now if I solve the equilibrium equation for this cut section, this is in equilibrium because the whole beam is in equilibrium. So if I write the equilibrium equation, what do I get? For this, I guess, so if I write the equilibrium equation for V, I get V minus PB by L equals to 0, which essentially means that V equals to P times B divided by L. Second expression for moment, what do I get? If I take the moment of the forces about here, now remember this distance is x because x is between A to C. So let's just go ahead and mark that one as well. So this is, this is my x over here. So for the moment, if I take the moment of the forces about this particular point, I have M minus the moment due to this force over here, PB by L times x equals to 0. So that gives you your bending moment as PBX divided by L over here. Now this force will not have a moment because I'm taking the moment at that point, right? So this is for the section 1. This is for the section 1 from A to C over here. Now let's go ahead and write the similar expressions for this section 2 over here. Now for section 2, you might be wondering whether it's easier to take from left to right or right to left from right to left, but for the sake of this problem, just to be consistent and just to show that we eventually end up at the same thing, let's just draw from the left to right over here. So now I'm going to draw or write the equations for the second section. Now the second section, the x lies between C to B over here. So in this case, your x lies between C to B. If I draw the free body diagram of the beam, what do I get? Let me draw a continuous line again. Suppose this is my beam now. I'm going from my left end all the way to the right end. So at A, I will have the same reaction that I had, that is PB by L. In between, now remember x is from C to B, so in between I have to cross this P somewhere at this point C. So let's maybe mark that point here somewhere over here where you have a vertically downward acting load of P, right? And nothing after that. So I'm going to go ahead and mark my shear and the moment. Again, since I'm going from left to right, my positive convention for shear is acting vertically down, and this is my moment which turns my beam into a trough or makes my beam smile. Okay, so for this free body diagram, now if I again go ahead and write the expressions. So the first expression for V, if I write, I have V minus PB by L plus P equals to 0, which gives me the expression that V equals to PB by L minus P, which can be further simplified as P times B minus L by L over here, right? And what is B minus L? L is the total length, B is this length. So B minus L or L minus B is A. So B minus L is minus A. So this is going to be equal to minus PA divided by L. So what we get V, let's just write a final neat expression that V is equals to minus PA divided by L. Now remember that when we are marking this shear and the moment over here, we are marking as per our positive convention that what kind of a what is the implication of the shear. It rotates the element clockwise, and the moment M makes your beam into a trough, right? the problem will tell you that whether while you're solving it, whether your convention was in the right direction or in the right sense or not. If you're getting a positive V, means that yes, the V indeed is acting there in the positive downward way as you have marked, right? Or if it is negative, then it tells you that no, at that point V acts in the opposite direction. But it's fine, as long as we are marking it properly in the diagram, it should be okay, right? And the next one, so we have calculated the expressions for the shear. So let's go ahead and write the expression for the bending moment now. Again, taking moment of the forces about this particular point. Again, I have M and I have this force here. Now remember, this distance again is x, because I'm taking x from all the way from left to the right. So let's just mark this one. This is x over here. And also remember one more thing, this P acts at a distance a over here. So let's just mark that as well. This is a, this distance is a. So I have, I'm writing the expression for the moment. So this is m, right? And the moment due to this particular force is going to be minus pbx by L. Then I have to account for the moment for this force. This acts in the same direction as the moment m is acting, so it is going to be positive. It is plus p into x minus a equals to 0 over here. And from that, if you simplify a bit further, what you will get is that m is pbx by L minus px plus pa, right? Okay, so now that we have these expressions for the section 1, the expression for the shear and the bending, for the section 2, the expression for the shear and the bending, let's go ahead and try to draw in this diagram over here. Now it's often easy when you're drawing the diagrams to have the parallel grid lines, so that you know where the discontinuities and everything are. So let's just go ahead and do that. By parallel grid lines, I mean that where this section A is, I'm just going to drop a line over here, and where this P is, I'm just going to drop another line over here. Where this reaction B is, where this support B is, I'm going to drop another line over here. So this is my beam. So this is my point A over here, this is my point B over here, and intermediate I have my point C, right? And similarly at the bottom A, I have C, and this is my B at this point. These are the points. Now from A to C, so the first one is my shear force diagram, and in the next one I'm going to draw my bending moment diagram. So for the shear force diagram, you have to consider the V's over here. So as you can tell that when x is from A to C, the value of V is a constant PB by L, which is quite intuitive. If you come to the left end over here, you see there is a vertical reaction PB by L, which automatically bumps up your shear, which is evident from this expression as well. So at A, I am going to have vertical shear, that is PB by L. It is positive. This comes out as positive, and in this one the upper half plane is positive and the bottom half plane is negative, both for the shear and the bending. So since it's PB by L, I have drawn it in the upper half, PB by L. Now interestingly, from A to C, when x is from A to C, there is no change in shear because it is independent of x. So from A to C, it is going to have a constant value. Now, interestingly, just after you cross the point C, remember, this is probably valid when you're just to the left of C, because here you have this discontinuity of P that is acting. So when you're going just to the right of C, when you're in this region, then the value of V drops to minus PA divided by L. So it becomes a negative over here. So that means that you are going on a constant line PB by L, right? And all of a sudden, just that after you have crossed this point C where this load is acting, you are dropping to a minus PA by L. So let's go ahead and mark that drop as well. So we are essentially having a drop, right? So this is PA by L. I'm not writing the negative sign because I'm drawing in the lower half plane, which is negative to begin with. And then from C to B, it remains a constant. You see, from C to B, this is also independent of x, so it remains a constant at a negative PA by L, which is again evident because if you are coming in and drawing as a constant minus PA by L, you see at B you have a reaction of PA by L, so it goes as a constant line and then goes up to meet the point B over here. So here is simply going to come and be like this over here, right? And then this is what you get. So this is the shear force diagram. Let's mark the positive and the negative. So you have the positive shear over here and you have the negative shear over here. Okay. Now let's go ahead and mark the bending moment diagram. Now intuitively remember what we had discussed, that this is a pin and this is a roller at the two ends of the beam where there is no externally applied moment at those points. So intuitively the value of the bending moment at those points A and B over here at the two ends of the beam must be equals to 0. Let's see if that is the case. So you get from A to C, your M becomes PBX divided by L. So essentially when X is 0, that is at A, you have a 0 bending moment. And when X equals to A, that is X is over here, right? Just to the left of C that you have over here. When X equals to A, the value of M becomes equals to PAB divided by L. So let's just mark it over here, that at X equals to A, I have the moment as PAB by L. And how is the variation? This is a linear function of X, so it is going to go from 0 over here to a PAB divided by L. So let's just go ahead and mark that for the bending moment. So this is what I get. This point here is PAB divided by L over here, right? Now, right after this point, when you are just cross the point C, then the expression for the moment is this. Right now, intuitively at B it should drop down to 0 because at B we have a roller. Let's see that when we put X equals to L. Now here remember X goes from here all the way to from C to B. So if you put at just for the sake of finding that out, so at X equals to L, if you put that, what do I get? I get that this L and this L will cancel, so I will get M equal to PB minus PL plus PA. Now if you take the first term and the last term, so this is becomes PA plus B minus PL. Now A plus B is nothing but the total length L over here, so PL minus PL, that becomes equals to 0. So it checks out, that one checks out. So it's going to be a 0 over here, right? Now let's see what is the value over here. So at this particular point, what is the value of X? At this particular point, the value of X is A, because I'm just trying to find the bending moment here. So X goes from C to B. So at this point, the value is A. So let's try to find that out. So at X equals to A, I get M equals to PAB by L minus PA plus PA, right? So you end up with PAB divided by L, which also checks out with what you had calculated previously, because there is no discontinuous moment which is applied there. So the moment at that point must be what you have calculated from the left and to the right. So it is PAB divided by L. And as you can tell, it's a linear function of X, PAB by L over here, 0 over here. So it must have a linear decreasing slope. Something like this over here. So the whole bending moment is positive. Shear force was a positive and the negative, and the whole bending moment is positive for this particular case. Now, just a few key takeaways from here is that can you guess the point where the bending moment becomes maximum? As you can tell, the bending moment becomes maximum over here. And what is the, how does the shear translate over there? See, at that particular point the shear goes from a positive to a negative over, so there is a transition. So we will discuss more on these intuitive analogies or the intuitive correlations or the links between the shear force diagram and the bending moment diagram later when we learn some of the relationships between these types of forces that is there. But I hope that this first simple example is clear. So after seeing this, maybe you want to try it out on your own. Now, this problem, as I said, we did by taking the section from the left to the right. Now, if I was taking the sections from right to the left, my V convention would change, right? But you will see we will end up with the exact same expression. So let's take a look at that as well. Right, so now we are going to take the same sections 1 and 2. Now, instead of taking from the left to the right, let's try to take from right to the left, and let's see if we get the same shear force and the same bending moment diagram or not. You should, right? But this is just to prove that you actually get it. So maybe we just, do it for this section, and the other one you can do and you can compute, and you will see you will end up with the same shear force diagram and the bending moment diagram. So let's talk about this particular section 2. So when we write the expression for the section 2 over here, remember for section 2 means, now since I am going from my right to the left, right? So my x is going from B to C. So x lies between B to C over here. So let me draw the free body diagram of this part of the beam. So if this is my beam over here, at the right end, this is my point B now. So at this particular point, I have the reaction force PA divided by L, right? From B to C, I have nothing else except that at C I have this load, but that's immaterial because I'm looking at, in between these 2 points over here. So if I have nothing else, I have nothing else to mark on top of this beam as well. So I will just draw the shear force. Now, since this is where it gets important, since I'm going from right to left, my positive convention, remember, positive convention is again the nature of action. So my shear tries to rotate my element clockwise. So the shear, the positive nature for the shear is this V over here, and my moment tries to make my beam into a trough. So this is my moment. Always remember, if you're taking, remember that small element that we had looked at previously, and I'm going to digress for a minute. That the small element that we looked at, that if you are going from left to right, the positive convention is this, and if I'm going from right to left, my positive convention is this, right? So here I'm going from right B or to the left, so this becomes my positive convention for the shear. The best way to remember that, the nature of action, V tries to rotate your element clockwise and M tries to bend your beam into a trough. So here, if you again write out the expressions for the V and the M, what do we get? For V, I get V plus PA by L equals to 0, which gives me V as minus PA by L. Does it check out with what we had done before? Yes, it does. You take a look here. When x between B to C, from B to C, there the value of V was a minus PA divided by L. So it did not matter that whether you took this section from the left to the right or you went from right to the left, you must end up with the same quantity. So you are getting the same quantity over here. Let's write an expression. Let's write the expression for the moment. So for the moment, now remember here, my x goes from here to here. So this is my x. Now, if I take the moment of the forces about this particular point, I can write that M minus PAX divided by L equals to 0, which gives your moment M as equals to PAX by L, right? Again, look that when you put x equals to B, this distance over here, when you put x equals to B, in that case your moment becomes equals to PAB by L, which is exactly what you had over here. You get a positive PAB divided by L at a distance B. At this distance B over here, you get a positive PAB divided by L. Now similarly, if you go ahead and write the expressions for 1, you will see that you will again start falling back into this shear force. So try it out. You just, instead of going from left to right as we did previously, go from right to left. We already wrote for 2, write for 1, and you will see that you will end up with the same shear force diagram and the same bending moment diagram as well, right? Okay, so this concludes our problem example number 1. Next we'll look at the example number 2.